Hello, my name is Dan Hulea. I'm a lecturer at Politehnica University of Timișoara, where I teach subjects of power electronics. Today I'm going to continue the presentation on hybrid DC-DC converters with focus on bidirectional topologies. I will start this presentation with a framework based on the classical bidirectional buck-boost converter, a framework which is useful for analyzing all the presented topologies. Then I will continue the presentation with state-of-the-art bidirectional DC-DC converter topologies analyzed in the same manner using the same framework. I will then continue the presentation with three bidirectional hybrid DC-DC converters with a switched capacitor converter, a switched inductor converter, and a combined switch inductor switch capacitor converter. All three are analyzed in steady state and dynamic operations, and experimental results are shown. I will also discuss about eventual challenges that appear in using these topologies. In the end, I will conclude the presentation with a comparison for all the presented topologies. Starting with the conventional buck-boost converter. This topology was chosen because it is a simple hard switch topology, it is well known, and it will be very relevant in the final comparisons. The schematics contain two voltage sources. As it is a bidirectional converter, it is a low voltage source on the left and a higher voltage source on the right. The current direction in the schematic represents a positive current for buck mode, which is current flowing into the lower voltage source from the higher voltage source, and a negative current for boost mode, which is current flowing from the low voltage source to the higher voltage source. Here we have a few assumptions in mind for analyzing the converter, assumptions which are going to apply to all the converters analyzed in this presentation. In the beginning, we have to consider that all components are ideal, and we have capacitors large enough to have considered a constant voltage. We have steady state operation for all converters and a continuous conduction mode. In order to analyze the operation of the conventional buck-boost converter, the equivalent schematics for the two switching periods are represented. Here we have the T-on interval such that the current increases in buck mode, and also the duty cycle is calculated for a simple representation of the conversion ratio for buck mode and D' for boost mode, even if theoretically they are related. We continue the analysis by representing the inductor voltage for the two switching intervals. Therefore, we can calculate the average inductor voltage, and because we have steady state operation, we can consider that the average voltage on the inductor is equal to 0. Next, we can express the voltage ratio with the well-known formula for the buck or for the boost converter operation. Next, we represent the main theoretical waveforms. Here we have the inductor voltage and current, the switch voltages and the switch currents, and the capacitor ripple voltages, which are very useful when designing the capacitors. For the inductor design, a method considering a current ripple percentage is chosen. So we start by choosing the ripple percentage. The ripple percentage is a ratio between the inductor current ripple and the average inductor current. Usually we choose values between 20% to 40%. We then continue by finding the relation between the inductor current and the output current on the low voltage side. And we see here that these two currents are equal, but this is not the case for all converters, of course. We can then continue by calculating the inductor voltage, which is the product between the voltage applied on the inductor times the time which this voltage is applied and divided by the inductor current ripple, which is calculated from the previous relation. And here we have the actual inductor value calculated for this converter. Because it is insufficient to compare a converter by the number of inductors or by the current and the inductance value just alone. So we use another performance indicator, which is the total energy stored in all the inductors for the converter operating at the rated parameters. This is the total sum for all energy in the inductors. For the classical buck-boost converter, this inductor energy is of course equal to the inductor energy on the single inductor because it only has one inductor. Next, we proceed by designing the two capacitors, and here we consider a constant current load on each side. So we choose a constant voltage ripple percentage for all capacitors. This is the same ripple percentage for all capacitors. We then consider the function for the inductor current as a function of time, because we need the inductor current for calculating the capacitor currents as time functions, which we then use by integrating these currents and dividing by the voltage ripple on the capacitors. We use these currents to calculate the voltage for the values for the two capacitors. As these values don't tell us much, we will use the same principle as before to calculate the total energy stored in all capacitors during normal converter operation. So we calculate the energy on each capacitor and then we add it up in the total capacitive energy. We use these two energies, the capacitor energy and the inductor energy, to express the volume of these passive components and their costs, which should be proportional to the value of the stored energy. We also have to take into account the switch requirements, so we use the total switch stress as a performance indicator. Here we use the nominal voltage that appears on a transistor and the nominal average current stress, even if in literature the peak or the RMS currents are used, but because the peak current is related to the ripple percentage, we can simplify the analysis just by using the average currents. And the final result is the sum between the product of the voltage and current for each device. This should also be related to the cost and the volume for these switching devices, as well as the efficiency, the total efficiency on the switching devices. I will then continue this presentation with state-of-the-art bidirectional DC-DC converter topologies, which are all analyzed with the same procedure as the conventional bidirectional buck-boost converter. We will then compare these topologies to the hybrid converter topologies, which are the main focus of this presentation. The first converter to be analyzed is a switched quasi-Z-source converter, which includes a Z-source impedance in its structure. In order to operate, this converter connects an inductor between two intermediate capacitors, which are then connected to the high voltage input capacitor at a different voltage. So this is important to remember, because we have capacitors here connected at different voltages together, and this might result in higher current spikes. With this being said, we calculate the voltage conversion ratio, and we see here that it has a much lower value than the conventional buck-boost converter for the buck operation mode, and a larger conversion ratio for the boost operation mode. And this is actually a desirable feature in many applications. We also calculate the total inductance energy, total capacitor energy, and the total active switch stress. But these indicators are a bit difficult to be compared to the conventional buck-boost converter in this form, and we will compare them in the final slides in the comparison section. Next, we have the conventional bidirectional quadratic converter. This consists of two series connected conventional buck-boost converter. So we have one converter on the left, followed by another converter on the right. The operation of this converter, I think it's quite clear from the two equivalent schematics, which are developed from the conventional converter as well. As the name suggests, this converter has a voltage ratio, a conversion voltage ratio equal to D squared for buck mode, and 1 divided by 1 minus D prime squared for the boost mode. And this represents a much wider ratio than the previous converter. We also calculated the performance indicator used in the final comparisons. Next, we have a bidirectional quadratic converter with a different schematic, but as we see, it has the same equations, the same mathematical characteristics as the previous schematic. Because even if this converter has a different schematic, the two equivalent switching schematics are identical or very similar to the conventional quadratic converter, at least in terms of electrical schematic. Next, we have a different bidirectional quadratic converter with a different schematic and also different equivalent switching schematics. This time the two schematics are also different, but as we see, the main mathematical results are the same as the rest of the bidirectional quadratic converters. Next, we have another bidirectional quadratic converter, which has a few additional diodes. in addition to the main switches. And because of the additional diodes, we actually have two different equivalent schematics for the T-off interval, and even if they are even if they seem very much different, actually the two equivalent schematics from the electrical perspective are actually the same. We have here the inductor connected to the ground, and here the inductor is connected through the diode also to the ground, so electrically we have the same connections. And because of this, we can expect to have the same mathematical results. Of course, because of the additional diodes, the total active switch stress is actually higher in this case. Next, we will have a look at a modular multi-level converter with a triangular shape. Here the author proposes to use more modules if the required voltage is higher, and actually each module should operate at 50% duty cycle, but here we stopped for a 6-switch converter just to keep the number of switches at a lower value. So because of the large number of components, the operation is slightly more complex, resulting in a wider voltage conversion ratio, which is similar to the quadratic converter. Even if it has a much different form, it is very close to the quadratic converters. But here we see that we have much more complex performance indicators, and they are very difficult to compare at this point with this form. So we will also take a look at the final comparison in the graphical form. Next, we have two bidirectional switched capacitors, which are different than the hybrid switched capacitor converters. These converters switch capacitors, and they are charged and discharged together at different voltages. So this is different than the hybrid converters, which switch capacitors and they connect them in parallel and in series, but they maintain the same voltage on each capacitor. So in this case, the operation might result in larger current spikes on the capacitors. We see here in the two equivalent schematics that these two capacitors are connected in series to the input, and then they are connected in parallel to each other, and the operation of the converter results in different voltages for these two capacitors. Because of this operation, the conversion ratio is limited at 50%. So we have to also keep this in mind when operating the converter. And here it is important to mention that even if we calculated the performance indicators, they are not taking into account the current spikes which might occur when operating the switched capacitors. Next, we have a different switched capacitor converter. Here, one of the two intermediate capacitors is connected to the low voltage input, and then is connected in series to the other capacitor at the higher voltage input. The conversion ratio is also limited to 50%, or of course 200% in the boost mode. But we see here that the conversion ratio as function of a duty cycle is different when compared to the previous converter. Also, the performance indicator here do not take into account possible current spikes which might occur. In the next slides, we will take a look at the first bidirectional hybrid switch capacitor converter. We see here that the schematic is inspired by the unidirectional design, which uses a switch capacitive cell composed of these two capacitors and the diodes, connected at the output of a boost converter, which we have here on the left. And the proposed bidirectional hybrid switch capacitor uses bidirectional switches in place of the diodes. We have these two MOSFETs which replace the diodes. We have therefore bidirectional operation. Here we see the two equivalent schematics which show us how the converter operates. So first, the two switches connect in parallel the two capacitors from the switching cell during T-on interval. This is the interval in which the current from the inductor increases in the buck mode. And then in the T-off interval, the two capacitors are connected in series at the higher voltage input through the second inductor. We can say here that the two capacitors are connected in parallel between the inputs, and in the second one, the two capacitors are connected somewhat in series to the high voltage input. Because the EL1 current is much higher than EL2 current, we can say here that the two capacitors are discharging in parallel to the low voltage side when operating in buck mode, or they are charging in parallel when operating in boost mode. And then on the T-off interval, the two capacitors are charging in buck mode from the high voltage source, or they are discharging in series to the high voltage source in the boost mode. Here we define the duty cycle in the same way. And then we can continue by writing the inductor voltages. And here we have to keep in mind that the two capacitors are considered identical, so the voltage on them is the same. We have the same voltage, and this simplifies the analysis. This converter also operates in steady state mode, so we have the average inductor voltage equal to 0, which helps us continue with our analysis, calculating the voltage ratio in buck mode, and we see that we have a better conversion ratio than the conventional buck boost converter, but of course not as low as the quadratic converter, which actually has an even lower conversion ratio for the buck mode. And we also see the conversion ratio in boost mode. And because we have the two switched capacitors, we can also calculate the voltage on these two capacitors, the voltage on each capacitor actually, which is the sum between the two voltages, the high voltage and the low voltage, divided by 2. And this voltage also gives us the value for the voltage stress on the MOSFETs. And this is actually lower than the conventional buck boost converter. Next we have the main theoretical waveforms, and here we see the voltage on the inductors, and then the two currents on the inductors, the voltage stresses on the transistors, the currents through the transistors, and here we see that the currents from one transistor is actually higher than the currents through other transistors, and the current ripple through the two capacitors has quite a large value. but this means that the current ripple through the other capacitors is much lower because we have the two inductors. Also in the bottom we see the voltage ripple on the on the 4 capacitor. Here we have the same voltage ripple on both the switched capacitors. We design the inductors in the same way. We consider the same current ripple percentage. This can be, for example, 20% or 40% of each inductor current. Then we find the relation between the inductor current and the output current. Here is the same as the two currents. Then we can calculate the inductor values and the energy for each inductor. In the end, we see that by calculating the total inductor energy, we actually have the same inductor energy as the conventional buck-boost converter, which is of course a positive aspect because this converter can achieve a much wider voltage range with the same inductor volume as the conventional buck-boost converter. Similarly, when designing a capacitor, we also select a ripple percentage for all capacitors, for example 1 or 2%, a much lower value. Then we can continue by writing the equations for the capacitor currents, and we see here that the switched capacitors have a larger ripple, also as we see in the waveforms. Then we can calculate the capacitor values and the energy stored in the capacitors, and then the total energy stored in the capacitors. We see here that the total capacitive energy is slightly higher than the conventional buck-boost converter. And this value actually depends on this ripple percentage of actually inductor current ripple percentage, which actually appears in the total capacitive energy. But as I mentioned already, this value has quite a low value, so it has a small influence. Therefore, the difference is quite insignificant. If the ripple percentage is even smaller, the current ripple percentage, therefore the total capacitive energy will also be closer to the total capacitive energy of the conventional buck-boost converter. So even if this converter has a wider ratio and 2 additional capacitors, the actual capacitor volume and cost is not much different than the conventional buck-boost converter. Next, we continue by calculating the total active switch stress. As we've seen before, the voltage stress is lower for these 3 transistors because it is only equal to the switched capacitive voltage, which is lower than the higher voltage from the converter, and this is an important difference comparing this converter to the conventional buck-boost converter. Then we've seen that the current stress is slightly higher on one switch and lower on the other 2 switches. And then we can calculate the total active switch stress. And maybe it is a bit difficult to see, but actually this total switch stress is lowered compared to the conventional buck-boost converter. but this we will see better in the final results. Next, we continue with the dynamic analysis. In order to operate the converter with a controller, we must perform the dynamic analysis. So here we include all parasitic resistances in the schematic, and then we use this for designing the dynamic model with the state space average method. Also in parallel, we developed a PSIM software simulation model which simulates the switch converter and also includes the actual circuit used in control. So for the PSIM simulation, we have all the switch components and the controllers used for controlling this converter. Here we have, at the beginning, two important transfer functions, which is the control to the one of the inductor currents and the control to the other inductor currents. And these are important because we have a bidirectional converter and we need to control the current at first, and maybe later we can think about controlling the voltage. But here the most important control is controlling the current. Usually for this we select to control the higher currents because it has a higher gain in the transfer function. Here on the right we can see the frequency responses obtained by the two methods. We have the simulation results here and the results performed with the state space average. And we see that the two sets of results are pretty much identical, even if the PSIM simulation achieves a much more closer results to the reality. The mathematical model, which is a simplification, is very close, and this is used to validate actually our mathematical model, because the PSIM simulation does take a lot of time to run, approximately 1 hour, and the state space average model can be calculated pretty quickly. So the state space average is validated, so we can use it to design the controller. Next, we continue to the first controller used for this converter, which is a Valley current mode control. We see here that it is a very simple implementation, and of course it is analog, it has a few components, but the good part is that it doesn't require any kind of tuning, so it is very fast to implement. We see here on the left we have some simulation results also done in PSIM, and we see a very good response for the current which we control. This is the IL1 current. We see that it doesn't have any kind of oscillation. And on the right we have experimental results which look very much identical, but these of course are experimental results done on performed on a real prototype. And we also analyzed the stability by watching the frequency response obtained from the PSIM simulation model. Next, we implemented a different analog controller. We used the same IL1 as control variable, but here we used the K-factor method for designing the controller. And why we did this is because how we see here in the results, even if the response of the IL1 current is pretty good, the second inductor current has some oscillations, so we actually have to slow down the controller on purpose, because if the controller is slower, then the oscillation on the second inductor are much slower. So as I've mentioned, here we have on the left some simulation results, and on the right we have experimental results, which also look pretty much similar to the simulation results. So as I've mentioned, the controller was designed using the K-factor method, and we see here the parameters used for design. We have the phase margin of 71 degrees and the cutoff frequency of 1.5 kHz. And this helps maintain a pretty low oscillation on the second inductor current. Next we have a digital controller, because in order to implement more complex control strategies we required a digital controller. For example, not just voltage control, but using this converter in a microgrid, there required some energy management strategies which can be more easily implemented on a digital controller. So this was used, and it was designed by directly shaping the body plot. Of course, because it is a digital controller, we are a bit more limited, so the phase margin was selected at 60.7 degrees at the cutoff frequency of 1.11 kHz. And of course, we also had to keep in check the gain margin at 10.5 decibels. Here on the left we see the simulation results, which show a pretty good operation and low oscillations on the second inductor current. And also I have to mention that this simulation also have the model of the microcontroller used to control the converter. So all the experiments presented before were acquired from this prototype, which is designed at a power of around 5 kilowatts with voltages of 400 volts on the high voltage side and 50 volts on the low voltage side. And we see here the switching frequency, which is 20 kilohertz, which might seem a bit low, but of course this prototype uses IGBTs and not MOSFETs, just in order to prove that the topology is not restricted by the switching devices. So this is the reason we built this prototype. And the tests were performed using lead-acid solar batteries. We see them on the left. Here is the converter. The batteries were used in place for the lower voltage, and on the higher voltage we have a DC source in parallel to a resistor. This is used to have a bidirectional operation on both sides. So the battery of course is bidirectional, and also on the other part we have the resistor in parallel to the source to have the bidirectional operation. Next we have the bidirectional hybrid switched inductor converter, which of course, as the name suggests, has a switched inductive cell which help the converter achieve its wider voltage range. Also in this case, the schematic is designed from the unidirectional design, which is a unidirectional converter in boost mode on the left and in buck mode on the right. And the bidirectional converter uses both of these topologies integrated into one. And of course, in place of the diodes, bidirectional MOSFETs are used. Now let's take a look at how this converter operates. And we see here the two equivalent schematics. During the T-on interval, the two inductors are connected in series between the two voltages, and during T-off interval, the two inductors are connected in parallel to the low voltage side. And here we consider the two inductors as being identical, so we also consider that because of the current is identical, we consider that the voltage on them is also the same. So mathematically, we can consider that we have only one inductor actually. By defining the duty cycle in the same way, and by writing the inductor voltages, which is, as I said, identical for the two inductors, we can calculate the average inductor voltage, and with this calculate the voltage ratio. And we see that even if this schematic is very much different than the previous converter, we see that the voltage ratio is the same. But here we also have two inductors, but we do not have the additional switched capacitors. So we might say that we have fewer components and we have the same conversion ratio as a result. Now let's take a look at the most relevant, most representative theoretical waveforms. And we see the same, the inductor voltages and the inductor currents. The switch voltage, which we see that it has a much larger value. And the other two switch voltages, which have a lower value. And then the switch currents. And we see here that the current ripple on the low voltage side has a much larger value than we expect on the conventional buck-boost converter. So we also have to keep this in mind when designing the capacitors. Then on the bottom we have the two voltage ripples on the two capacitors. Next, for the inductor design, we have the same procedure that we have on the previous converters, but also it's a bit simpler because we have identical inductors. First, we have to consider the same ripple percentage on both inductors. Then we calculate the relation between the inductor current and the low voltage side current, which now that we see this, we realize that the inductor current is actually lower than the output current. And this is helpful when designing the inductors, because if we have applications with high currents, it is easier to design inductors that work on lower currents. Then we can continue by calculating the inductor values and their energy and the total inductor energy. And again, even if this topology is so much more different than the conventional buck-boost converter, and even is different from the bidirectional hybrid switch capacitor converter, we have the same inductor energy, the same total inductor energy as the conventional buck-boost converter and as the bidirectional hybrid switch capacitor converter. Also, this is an important aspect to keep in mind. The two capacitors have the same ripple voltage percentage, but we see here that the two capacitors have quite some large current ripple. We can calculate then the capacitor values using these currents, and finally the capacitor energy and the total capacitor energy. So even if we have some large current ripples on the two sides, actually the current ripple on the input is lower, and this results in a smaller total capacitive energy for this converter. So actually overall the capacitors are smaller for this converter, compared to the conventional buck-boost converter. Also, we see here that the inductor ripple percentage is not present in this relation, so this is also an important aspect to keep in mind. Next, let's continue by calculating the total switch stress. Here we see that the voltage stress on one device is double than the voltage stress on the two other devices. And then we see that the current stress is the same as the conventional buck-boost converter, but actually it is smaller because the inductor current is smaller for this converter, so we actually have a lower current stress for this converter. And then we can calculate the total switch stress, which results the same as the bidirectional hybrid switched capacitor converter, lower than the conventional buck-boost converter. So even if this topology is different and it operates differently than the bidirectional hybrid switched capacitor converter, it has the same total switch stress. Next, we continue by analyzing the dynamic operation of the converter, which is performed in a similar way. We insert parasitic resistances in the equivalent schematic, and then we analyze this schematic with the state space average method. And of course, the initial switching schematic, we analyze it in PSIM software simulation, where we obtain the frequency responses of our transfer functions. Here, because the two inductors are identical, we actually have a simplified equivalent model. It is as simple as the conventional buck-boost converter, just because the two inductors are the same. Also, for the frequency response, the simulation contains a detailed model of the microcontroller. So this is the reason we have here multiple responses. First, we have the model simulation, and then on the top we have the frequency response of the SSA model in continuous time space, and then we discretize the model, and then finally we introduce the additional details also in state space average, so that is similar to the model simulation realized in PSIM software. So our discrete model is pretty much similar to the converter controlled by the microcontroller with all the additional details implemented in the simulation. Next, we continue by designing the digital controller. We directly shape the body plot in order to design the controller. We achieved a phase margin of 68.5 degrees at the cutoff frequency of 1.55 kHz with a reasonable gain margin of 13.8 decibels. And we see here that the simulation on the left are pretty much identical to the experimental results on the right. And this might not look like experimental results, but there are experimental results. And there is actually a difference in the transient operation here. The simulation is a bit faster. The model in simulation is faster than the model in the experiment, probably because in the experiment we have a few more parasitics which we have to take into account for closer results. But nevertheless, the two models, the frequency responses of the open loop of the controller and the model are pretty much similar in the simulation and the state space average model. For this converter, two prototypes were built. On the left, we have a prototype with conventional MOSFETs, with silicon MOSFETs, and on the right, we have the converter with gallium nitride devices. And both of them have a power of 3 kilowatts. Here we have the rest of the parameters. On the high voltage side, we have a voltage of 300 volts, 60 volts on the low voltage side, and the converter operates at 40 kilohertz. We choose this switching frequency because it is optimum for silicon MOSFETs, even if the GaN devices could operate at higher frequencies. But we wanted to see how much of improvement we can get in efficiency by using these gallium nitride devices. We see here that the two inductor currents are lower than we would expect on a conventional buck-boost converter. Here we have 30 amps, even if usually for a 3 kilowatts converter we would expect to have at least 50 amps on the low voltage side. But here we have only 30 amps, so this way we know that the switches have a lower current. Here we see on the left the equivalent model for the test setup. We have the converter here on the middle. On the left we have some supercapacitors, some Maxwell capacitors of 63 farad at a maximum voltage of 125 volts. And on the right we have a constant voltage load and a DC source in series to a diode. And we use this combination in order to have a bidirectional source here. And next we analyze the efficiency for both converters. On the left we have the buck mode, and on the right we have the boost mode. On this column we have the MOSFET prototype, and we see that the experimental results are close to the theoretical results, at least at higher power levels. The efficiency here is at a maximum of 96%, but on the boost mode we see that the efficiency is lower, of only around 90%. So we see quite a bit of discrepancy between the theoretical efficiency and the experimental efficiency. On the lower side, we see the distributions of power in the switching devices. We have the switching losses on the two switches and the conduction losses. And the same we have here on the boost mode. Next, for the GaN prototype, we see that the efficiency is much higher in buck mode. It is around 98%. But also lower in the boost mode, around 96%, and also we have a difference between the theoretical analysis and the experimental results. So the difference might be because the phenomena of shoot-through might appear, or because we have to take other additional aspects into the theoretical analysis of the converter. We also have seen some issues on this topology. We see here on the left simulation results and experimental results on the right. We have the two inductor currents and the two inductor voltages. And we see here that we have some oscillations on the two inductors. Of course, they are complementary because these oscillations appear when the two inductors are connected in series. And this might be an aspect which we expected. We see here that the oscillations are higher in the experiment, and they are a bit difficult to actually predict precisely because these oscillations appear because of the capacitors, of the parasitic capacitors of the switches which we know that vary pretty much with the voltage on the transistors. And also another issue is that this converter has a high frequency voltage between the two inputs, between the grounds of the two inputs. So this might result in a high electromagnetic interference. So this problem has to be eliminated. And we actually have an improved version of this converter, which has a DC voltage between inputs and no inductor voltage oscillations. And this was done using or achieving the same performance indicators. Even if we change the topology a bit, we have the same total active switch stress. And this new topology will be presented by my colleagues. So next I will continue with a combination between the two previous topologies, because we've seen some good results from the two topologies. So we tried a combination between two, and we achieved a combined hybrid switched inductor, switched capacitor converter. We see here the schematic of this converter. It has the switched inductive cell on the low voltage side and the switched capacitive cell on the high voltage side. Now let's see how this converter operates. We see here that during T-on interval, the two capacitors are connected in parallel and the two inductors are connected in series. And during T-off interval, the two inductors are connected in parallel to the low voltage side and the two capacitors are connected in series, and they are somewhat in series to the low voltage side, between the low voltage side and the high voltage side, while the two inductors of course are connected in parallel to the low voltage side. The same assumption as previous is valid. So the capacitors are here, they are discharging in parallel to the low voltage side in the buck mode, or they are charging in buck mode, or they are charging from the low voltage side in boost mode, and they are discharging to the high voltage side in boost mode, or they are charging from the high voltage side in buck mode. And also during T-on interval, the inductor currents are increasing for buck mode, and they are decreasing in the T-off interval. The duty cycle is defined in the same way. Therefore, we continue by analyzing the inductor voltages, and here we have additional assumption that the two switched inductors are considered identical, so we have the same voltage on them, and the two capacitors are considered identical and they also have the same voltages on them. Next, we can calculate the average inductor voltages, and considering a steady state operation, these average inductor voltages are equal to 0. So we calculate the voltage ratio, and here we see a much wider voltage ratio. It is quite close to the quadratic converters, even if it's not so clear in this form. And we can also calculate the switched capacitive voltage, and here we see that it has the same relation as the bidirectional hybrid switched capacitor converter. The switched capacitor voltage is half of the sum between the two voltage inputs. Next, we will have a look at the theoretical waveforms. Here we have the voltage on the L1 inductor or the switch inductors, and the voltage on L3 inductors with the voltages on the switched on the transistors, on the switches. Then we see the currents on the switches. We see voltage higher and lower for the two groups of transistors, and the same with the currents. And then we see a even much larger current ripple for the low voltage capacitor, and also we see a relatively large current ripple on the two switched capacitors, the regular inductor currents, and the voltage ripples on all of the capacitors. Then we continue to design the inductor. We keep in mind that we have two equal inductors, but the ripple percentage, the inductor current ripple percentage is the same for all inductors. Then we calculate the currents from the average currents from the inductors, and we see that the currents for the switched inductive cells are lower, and this is also again helpful. We continue by calculating the inductor values and the inductor energies, and again the total inductor energy. We see again that even if this topology is different, the total inductor energy is the same as the conventional buck-boost converter and the two other hybrid topologies. So even if this converter has a much wider ratio, it has the same total inductive energy. We continue now with the capacitor design. We have here the same voltage ripple percentage for all capacitors. And then we write the capacitor currents, which help us calculate the capacitor values and their capacitor energies, resulting in the total capacitor energy, which very interestingly is an identical energy to that of the conventional buck-boost converter. So again, this is a much more different topology, wider ratio, but the same requirement for capacitor volume, let's say, or same requirement for capacitor cost. We calculate the total switch stress in the same way. Here we see that two switches have a higher voltage and two switches have a lower voltage compared to the conventional buck-boost converter, and the same thing with the currents. Two currents have higher values and two switches have higher values for the currents, and two switches have lower values compared to the conventional buck-boost converter. But finally, the total switch stress results in a lower stress for the conventional buck-boost converter, even if it has 4 switches in comparison to 2 switches of the conventional buck-boost converter. This converter has a smaller total switch stress, which we might expect to have either cheaper switches or a better efficiency because of the switches. Next, we analyze the dynamic analysis, and here we also performed the analysis in the same way. We inserted the parasitic components and we made the model using the state space average method, and also we simulated the converter using PSIM software simulation. And even if this converter has a more complex model because of the additional capacitors and inductors, which all result in more state space variables. We can simplify the design by considering the two switched inductors as being one and the two switched capacitors as being one component. So this complex model can be simplified a bit, but indeed the controller design is a bit more complex because of the complex model. And then we take a look at the frequency responses, and yes, indeed they are slightly different, but even so the state space average model can be successfully used for designing the controller. Here we also used IL1 as control variable because it has a larger value, and we also took into account the oscillations that appear on the other state variables like IL3 current or the two switch capacitors, and we see that some damped oscillations are indeed present, but paradoxically it was a bit simpler to design the controller for this converter compared to the bidirectional hybrid switch capacitor converter. Here we also see a small overshoot for the controlled inductor currents. Actually, here there are both currents shown, even if only one of them is used as a control variable. And the controller was performed similarly by directly shaping the body plot, the frequency response. Here we have the open loop frequency response for the two models, for the state space average model and for the simulation models, and also the results on the left are simulation model and not experimentally. Here we see that we have a phase margin of 83.5 degrees at a cutoff frequency of 20 kilohertz, so it's quite a fast controller. But even with such good results, we see here some experimental results performed on the low power prototype with voltages of below 100 volts and currents also much below 100 amps. So we see here some oscillations on the inductor voltages. We have one inductor voltage here in red and the inductor current in blue. Also in the interval when the two inductors are connected in series. And then we see the third inductor current, IL3, which of course doesn't have the same oscillation, and we see here the IL3 inductor voltage. So even if this converter has very good results, we have still to improve this topology to remove the oscillations in the similar way we remove the oscillation from the hybrid switched inductor converter. Finally, we have arrived at the section where we compare all the converters with a graphical representation of the main performance characteristics for each converter. What are the performance indicators again? So first we have the voltage conversion ratio, which is the ratio between the two voltages as a function of duty cycle, both in buck mode and the boost mode. Then we have the total inductor or the total capacitor energy, which is correlated to the size and costs of these components. And finally, we have the total active switch stress, which is also correlated to the cost and efficiency of the switches. So as you will see, apart from the voltage conversion ratio, all these indicators are represented relative to the conventional buck-boost converter in order to have a simple or a more relevant representation. In our list, we have 12 converters. The first one is at number 0, the conventional buck-boost converter, followed by our hybrid converters. We have the last one at number 1, the bidirectional hybrid switched inductor switched capacitor converter. Then we have the bidirectional hybrid switched inductor converter, the bidirectional hybrid switched capacitor converter. This is number 1, because we also have a second hybrid switched capacitor converter, which will be presented by my colleagues. And then at number 5, we have the bidirectional switched quasi-Z source converter. At number 6, we have the conventional bidirectional quadratic converter, followed by the 3 other bidirectional quadratic converters. Then at number 10, we have the bidirectional triangular modular multi-level converter, followed by the last 2 switched capacitor converters. So here on the graph we have the step-down conversion ratio. With the black line we have the conventional buck-boost converter, which let's say has the worst step-down conversion ratio because all of the rest of the converters have a lower conversion ratio, which is desired in the buck operation mode. So now, if we look at the lowest conversion ratio, we see here that the quadratic converters from 6 to 9 have the lowest conversion ratio, and then they are closely followed by number 10, the triangular modular multi-level converter, and then we have the number 1, which is the bidirectional hybrid switched inductor converter, which also has a quite low conversion ratio. Then on the middle, with the blue line, we have the rest of the hybrid converters from number 2 to 4, and we also have the switched quasi-Z source converter with the same conversion ratio. Then we have the 2 other switched capacitor converters, which are limited here by at the 50% conversion ratio. Here we have to keep in mind that this conversion ratio is for the step-down mode, which is the ratio between the low voltage side to the voltage on the high voltage side as a function of the duty cycle D. This is relevant because next we look at the step-up conversion ratio, which is defined a bit different as the ratio between the high voltage divided by the voltage on the low voltage side. And this is as a function of D prime duty cycle. This is done in order to compare these converters to conventional unidirectional boost converters, so we have similar conversion ratios. Here we see almost the same thing. The faster the function increases, the better it is to be used for a wide voltage conversion ratio, because it can achieve higher conversion ratios at lower duty cycle. So here we see the quadratic converters, all the quadratic converters. Then we have again the triangular multi-level converter, and then we have the bidirectional switched inductor switched capacitor converter, followed by the rest of the hybrid converters here in the middle, together with the switched quasi-Z source converter. And here we also see one of the switched capacitor converter, and then the other switched capacitor converter going pretty close to the conventional buck boost converter. But we have to keep in mind here that the two switched capacitors are limited by a conversion ratio of 2. They cannot go lower, even maybe if this is not required, but they cannot go lower at 1 compared to the rest of the converters. So on this slide, we take a look at the total inductor energy, which is actually the ratio between the total total inductor energy and for our converter and the total inductive energy for the conventional buck boost converter. And if this ratio is higher than 1, then the converter studied requires more inductive energy, and if it's lower than 1, it requires less inductive energy compared to the conventional buck boost converter. And we see that this ratio is a function of the conversion ratio in buck mode, not as a function of the duty cycle. Here the lowest we see are the two switched capacitor converters, and we have to remember that for their analysis we do not take into account the current spikes resulting by switching the capacitors at different voltage levels, so we also have to take this into account. Then from 1 to 4 we have our hybrid converters, which have the same requirement for inductor energy as the conventional buck boost converter. Then at number 5, requiring much higher inductor energies, is the switched quasi-Z source converter, which requires, for low conversion ratio, we see here that it requires inductors with even 40% more volume compared to the conventional buck boost converters or to the hybrid converters. Next, with almost 60% more inductor energy, we see the quadratic converters. All the quadratic converters require the same inductor energy. And finally, with almost 80% more, we have the triangular modular multi-level converter with, of course, almost 80% more inductive energy. The total capacitor energy is represented in the same manner relative to the conventional buck boost converter, as we see here, as a function of the conversion ratio in the buck mode. And we see here that the lowest requirement for capacitors is for the last switched capacitor converter. But again, this does not take into account the current spikes on these capacitors. And then we have all of the hybrid converters, and we see that they are very close to the conventional buck boost converter. We have lowered the switched inductor converter, which requires a lower volume of capacitors, and then at 1 we have the combined switched capacitor switched inductor converter, and then above 1 we have the two hybrid switched capacitors converters. And this difference is coming from the inductive ripple ratio. Therefore, if we decrease the ripple ratio, then these three lines will be closer, and if we increase the ripple ratio, then the difference will also increase. Now, the ripple ratio, the inductive ripple ratio considered here is 20%. So this is a regular value, and we see how the difference look in this manner. From my opinion, the difference is not very significant, so we can consider them as being almost the same. Next, if we look on the graph, we see that the total capacitive energy for the quadratic converters is much higher. We see here almost 60% more for a low conversion ratio of let's say 6 or 5%. And then we have the triangular multi-level converters, which is here, followed by the switched quasi-Z source converter. And finally we have the first bidirectional switched capacitor converter with the highest requirement for capacitor energy, also without taking into account the high current spikes which appear for this converter. Here we see the total active switch stress, which is also represented relative to the conventional buck-boost converter. Here we see that the lowest stress is for the combined bidirectional hybrid switch inductor switch capacitor converter, which is then followed by the quadratic converters for a low portion, because then we have one of the switched capacitor converters at number 11. But here we have to keep in mind that that this converter does not take, or this analysis does not take into account the current spikes which might occur by connecting the two capacitors in series and charging them. Then we have the rest of the bidirectional hybrid converters, or at least the switched inductor and the switched capacitor converter, together with the switched quasi-Z source converter with a much lower conversion ratio compared to the conventional buck-boost converter. And then we have the triangular modular multi-level converter, followed by the other switched capacitor converter. And then we have the second hybrid switched capacitor converter, which has a slightly more stress on the devices because it actually has additional switches. So this is why it has a higher total active switch stress. And finally, at number 9, we have the second the final quadratic converter, which has additional diodes. Therefore, by having additional components, it also has a higher total active switch stress. We see here rising almost to 80% more than the conventional buck-boost converter. So, in conclusion, we see that there are multiple bidirectional wide ratio converters available, each with a wider or narrower conversion ratio, and each having different requirements in terms of inductors or capacitors or transistors. But overall, the hybrid converters have good characteristics and are a good choice where wide ratio converters are required. Even so, for all converters, important technical aspects must be considered, such as voltage oscillations or series connected inductors, current spikes on parallel capacitors connected at different voltages, or even the controller design procedures if we have a more complex model. Finally, we have a list of the most relevant references. So this was my presentation. Thank you for watching, and I wish you all the best.